So, as I was saying, I'd like to welcome everyone to Daniel's Relatorium talk, which is going to start momentarily, and Edmund Harris will moderate. I just wanted to start by saying, well, first of all, this is going to be the last talk of the year. Obviously, we're almost, well, we made it through the whole year, which is a great accomplishment for us. We're very proud of how far this little initiative has taken us, and we look forward to another year of new talks once a month, the last Friday of every month, roughly is what we try to do. So if you're interested in participating, don't hesitate to reach out to one of us through our YouTube channel. And we're in the process of putting together our talk series for the next year. In the meantime, I wanted to also point you to the session we are organizing at the upcoming JMM in a couple of weeks. So and maybe I'll put um, uh, the website in the chat for anyone who wants to look it up. So we have a day, Friday, January 10th, devoted in the morning and the afternoon, a session on methods of compassionate mathematics with a quite wide selection of speakers. While I have your attention, I would also like to point out that we have also, we're in the process of organizing a session later on in the spring in April. It's a session in the AMS sectional meeting in Hartford, Connecticut, which we're in the process of inviting people for. So again, if you're interested in participating, if you have some ideas about it, don't hesitate to reach out to one of us who are organizing it, and we'd be happy to send you more information. With that, I'm very happy to pass the mic on to Edmund and Daniel for what is going to be a very wonderful, interesting talk. Thank you.
Well, welcome everyone. So I'm really happy to introduce Daniel, and who's been a long-standing member of the compassionate math community. So the talk is on the topic of sort of straight lines and small numbers, and what happens when you put together small numbers of straight lines with certain rules. And I think, like many people, when I first came across complex numbers, a natural question emerges: sort of, what happens if you do that again? And then you might learn about things like quaternions, and maybe you've heard terms like octonions. And I think naively you sort of think, well, what is the system that these things are operating within? And I think this is a sort of good way to approach any area of mathematics when you start finding a bunch of examples that seem to have interesting similar properties. Ask yourself what happens when we play with them. And I think that's a question that's gone in various directions through the history of math. But I think Daniel is looking at it from an interesting point of view, especially that question of like generalized complex numbers and quaternions and things like that. So I think that's a good place to sort of think about as I let Daniel begin.
Thank you very much, Edmund. That was wonderful. I appreciate the introduction, and I'm very excited to share with you this little seminar talk that I've prepared. First of all, I just want to say it's Christmas time, so Merry Christmas or Happy Holidays, and please grab your hot beverage of choice. This is going to be very much on the recreational side of math talks, I hope, and it should be a fun journey. So let's not waste too much time. I will share my screen so you can see the slides. So here we go. I hope that's all visible. So like Edmund was saying, this topic of hypercomplex numbers was one that I've always been very much drawn to. And It's kind of a niche topic, I would say. If you've never heard of the concept of a hypercomplex number, don't feel bad. It's there are obviously several different names as well that some of these ideas are called, and maybe you're familiar with them by another name, which I'll get to in a second. But essentially, I've kind of done this work for quite some time on the side. This is completely a side project, a passion project of mine. And it started out with me programming. My background is in computer science. And I've always enjoyed creating computer graphics and visualizations. And for that purpose, you often dabble around and write your little linear algebra library with some vectors and some matrices. And then over time, once you get a hang of that, you might go looking for what other algebraic structures are there that could help me do even more things, even more interesting and more general things. And that's kind of what led me down this path. And this is what I would say is the culmination at this point of my work, as I explore, more and more general approaches, and kind of try to be more open in terms of what does it mean to be a number. So like Edmund was saying, for a bit of historical context, in the 19th century, there was a little bit of an explosion of different number systems once people discovered the complex numbers and saw how useful they could be, basically coming from the desire to solve certain equations, find solutions to certain equations. The natural next question was, well, what can we do if we extend this construction further? What if we add even more types of numbers? What will that allow us to do? So people invented all kinds of different number systems, some more better behaved than others. And eventually the situation just became such that people decided, well, we need a general approach to study them. And that's where the concept of a hypercomplex number was born. Again, this is not a very mainstream term, I think, and we will go over that in a little bit. But I think it's a very nice and fitting term for what I will be talking about. And I would really like for it to become more widely known. So maybe this seminar will play a small part in that. But as you can see, these things have been around for a while, and textbooks have been written. The first one is pictured on the slide, and it was later translated to English as well, so you don't have to speak Russian to read it if you would like. And in that textbooks, the definition given for a hypercomplex number is as an element of a unital, but not necessarily associative or commutative finite-dimensional algebra over the real numbers. And largely, this is the definition that I'm going to use. But of course, this is not a very useful definition if you don't already know what an algebra is over the real numbers. So we will go ahead and tease that apart a little bit. But essentially, if you come from an abstract algebra background, the modern use of terminology is referring to these things as algebras over fields. And in particular, for all of the examples that I'll be looking at, they will always be over the reals. And so going down this path that Edmund described, of taking complex numbers and asking the question, what happens if we add more more basis elements to our algebra? Yeah, that's where you arrive. So essentially, we have a structure that has some coefficients, which I usually will denote with a superscript x0, x1 to xn, and we have some basis consisting of I0 through in, and if the algebra is in fact unital, which means it contains a unit, then that unit will typically be just denoted as 1. And it is convention to choose the basis such that the basis vectors typically square to either -1, 0, or +1. But I don't necessarily think this is important. So for the most part, I'll be talking about algebras where you can have any kind of basis vectors and any kind of value that they're squaring to. So just to give you a little bit of context, if you do have a background in abstract algebra, just to help situate this talk, in abstract algebra, we're interested in developing these structures by starting out with a very simple structure of a set, which essentially is just a bunch of things, and there are no operations that we can perform. And then we kind of ask, what are the implications if we start adding more operations and also more requirements on those operations. So it's an interesting kind of balancing act where on the one hand, we're like expanding the possibilities by having more operations, more things that we can do with the elements of the sets. But at the same time, we may also require certain algebraic properties to hold, which again kind of reduces the amount of possibilities. So it's this interesting balance. And in order to get to K algebras, which are down there at the bottom, as you can see, it's useful to already have gone through some of these other structures that they're building on. But I hope that in this talk, I can keep things fairly simple. And in particular, if you already have a background, some background in linear algebra and know roughly what a vector space is, then the K algebras are just one step away. And it's a very natural step, in my opinion. So once again, if you're interested and want to find out more about all these different structures, it's quite the rabbit hole you can go down. I've just taken this screenshot from Wikipedia to show, again, kind of the hierarchy of these structures, how, we start out with very simple ones, and by adding more sets and more operations, you end up with more and more sophisticated structures. And yeah, like I said, it's very interesting and fun to study these things and the implications of them. And in this talk, we will be looking at the algebra-like structures in particular. So just in case you want to see, you have a mathematical background and you just want to see some rapid examples, here are the most famous ones, I would say. So typically people are introduced to these ideas by asking, various ways in which we can extend the real numbers. And in particular, there is this Cayley-Dickson construction that you can apply to generate the complex numbers, the quaternions and the octonions, and so on. And you can see how as you kind of increase the dimension of the algebra that you're working with, fewer and fewer algebraic properties hold, which you can either see as a problem, or maybe you can see it as a feature, not a bug, because having this additional flexibility allows you to do things that you couldn't do with the simpler structures. Another family that's very important are the Clifford algebras. And again, you could give a whole talk on them. I will not go into too much detail. I just want to point out that, like with the Cayley-Dixon construction, it starts with the real numbers, the complex numbers, and the quaternions, but then you end up getting various combinations of 2x2 matrices and with elements in those fields. So this is another very interesting family with some interesting applications. And the implications...
Daniel, we've got a quick question from the chat. So do hypercomplex numbers refer to everything below the complex numbers? This was asked when we had the Dixon.
Right. So I'll go through the precise definitions, but just to address the question, all of these I consider to be examples of hypercomplex numbers. So as you will see, there is a definition that's very general of what a hypercomplex number is, and the real numbers, complex numbers, and quaternions already fall within that definition. So the hypercomplex numbers are not necessarily anything that's more complicated than the complex numbers, but of course the name suggests that there is a straightforward path to generalizing them to higher dimensions, and yeah, all of the examples that I've shown so far will end up being specific examples or instances of the more general concept of hypercomplex numbers. I hope that answers the question. So I just want to speak a little bit on my personal background and motivation. Like I said, I'm not necessarily a mathematician by training. I studied computer science, and in particular, I discovered a passion for computer graphics and visualization, and that's where these things come up very naturally. And for the most part, in the kinds of applications that you may be familiar with, we're talking about Euclidean geometry. Everything is typically flat and made of triangles. And in that case, you get away with just regular old linear algebra. You have your vectors and matrices representing linear transformations. And perhaps if you get really into that, you may also encounter quaternions as a nice way to represent orientations in 3 dimensions. However, most people probably don't need to go much further than that. However, if you do the kind of computer graphics that I like to do, for instance, some information visualization, oftentimes you do want to go further because you want to display your data in a kind of mapping, in a spatial mapping that makes sense for the data, and you end up working with spaces that are curved or have other non-Euclidean properties. And in that case, you do kind of need to figure out a way to work with them. And that's where these hypercomplex numbers really turn out to be really useful. So like I showed in the previous slide, the spherical geometry is one example, but you can go even further, and there are interesting visualization techniques, for instance, like this one here, that utilize hyperbolic geometry in order to embed and visualize complex data sets, and the properties of that geometry make it such that it is a very natural choice when you have complex networks or graphs or trees with lots and lots of children, because you can just fit the data much better into a space like that. So
Daniel, another question going back to the discussion of what these things are. Can you say anything about how they relate to the surreal numbers?
So yes, the surreal numbers, as I understand them, are a step beyond what we will be talking about here. So if you want to kind of put it somewhere in terms of complexity or power, I suppose, then you would have, complex numbers. You would have the real numbers, complex numbers. Then you would have all the hypercomplex numbers, and the surreal numbers are even a little step beyond of what we will be talking about.
Is it true that all these examples are contained within the surreal numbers?
Yes, I think there is probably a way to do this mapping, because again, the way that I understand the surreal numbers is that they're mind-bogglingly large and quite yeah, quite a complex structure to get your head around. So I would imagine that there's a way to find a mapping from some of these into the surreal numbers and back. So, but again, this is less about extending the numbers, because the one way that I think about, and again, I'm not an expert on the topic of surreal numbers, but one way that I think about the surreal numbers is like extending to quantities that are kind of in beyond infinite, and then quantities that are below infinitesimal. Basically, extending the numbers as far as you could possibly extend them. So there are some interesting connections here that I will present to infinitesimals, and using these numbers to do differentiation. But I think at the end of the day, the surreal numbers are a step further than what I'll be talking about.
Thank you.
You're welcome. So yeah, you have interesting curved spaces, and of course, another question that arises if you are mathematically inclined is, how do some of these things, the notions that we're familiar with from 3 dimensions, generalize to higher dimensional spaces? And there also, it turns out that this notion of a hypercomplex number turns out to be really useful. So if you're thinking about how can you generalize spherical 3-dimensional space to higher dimensions, well, the hypercomplex numbers give you a good handle on that. So they are very natural in that sense to generalize. And that's, I think, the best justification I can give for the use of the term hyper in front of the complex. They don't necessarily have to be high dimensional, but it is very natural to generalize them. So yeah, those were great questions. And before we get even more questions, let's just get into the theory for a little bit and define what it is that we're talking about. So like I said, the K-algebras, which is what I'm kind of mostly talking about, are one step away from vector spaces. So just to establish some conventions, in your vector spaces, you will have your set of scalars, which I will just denote using regular letters, X, Y, Z mostly. You have your vectors, which I will use bold letters and lowercase to denote, and you have matrices, which are kind of uppercase, bold, and more generally, you have arbitrarily ranked tensors, but unfortunately, there is no way to go further than uppercase, so I just usually use uppercase letters for those as well. And one notation that's very useful when working with these structures is this index notation. So I will use, as I said earlier, subscript and superscript indices to refer to the coefficients or the components of the vector. And I will use this convention that's very common in differential geometry, tensor calculus, that if there is a repeated lower and upper index, that means that there is really a summation over all the values. So usually the indices will range from 0 to n, where n is the dimension of the space that you're working in. And as if you see them side by side, again with the lower and the upper index being repeated, then it just means a summation. But don't get too hung up on the notation if you're not familiar with it. It takes some getting used to, and part of the purpose of this talk is to show some other ways that you can think about it that are maybe more accessible. So just repeating from the previous slides, we will think of our vectors as linear combinations of basis vectors and scalars. And so you can think of it in two different ways. One is kind of using this index convention, index notation, and Einstein summation convention. And the other one is more traditional, using the brackets and kind of inner product to represent essentially the same information. And yeah, so given this vector space where we have scalars and vectors, now the question is, what is an algebra? Why is there any difference? What is the new ingredient that's introduced? So an algebra over a field K is just a vector space equipped with a bilinear product. So really, that's the most general notion that you can introduce. So essentially, when you go back again, in your vector space, you have these scalars and vectors, like I said, and there is multiplication among the scalars, and there's a way to multiply a vector with a scalar to get another vector, and you can multiply on the left or on the right. It doesn't really matter. The operation is essentially the same. But for some reason, typically, there is no way to take a vector and another vector and multiply them and get a vector as a result. So the whole remainder of this talk is really just about the implications of what if we introduced such an operation, what are the implications, and what can we do with it. And so this additional condition of bilinearity is very useful, because it means that just like with linear transformations, we can represent we can package all the information that's needed to describe this operation into essentially an n-cubed array of scalars. So on the computer, if you're implementing this, all you need is a three-dimensional array of floating point numbers, and you can already go ahead and do some computations. So it is sufficient to just say what the multiplication does on your basis, and that naturally extends to what it does to a general linear combination of your basis vectors. So just to make that point really clear for those who have a background in linear algebra and are comfortable with matrix multiplications, if you really wanted to, you could write this down in this way, and you could perform the multiplication basically by just pulling one of your vectors into the square brackets and then multiplying things out just the way you would multiply a regular matrix by a vector, which would result in another matrix, and then you just do another multiplication, and then you end up with your final result. And every kind of hypercomplex number will have this set of structure constants C, which determine what the multiplication should be. And just on the last line, notice how on the bottom you have 0, 0, and then you have x 0, y 0, and then you have 0, 1, x 0, y 1. So in a way, there's some really nice structure there. And we will exploit that when we write things later on in a more concise, in a more graphical way. So this information is a little bit tricky. I don't really recommend you kind of try to work with this in this particular way. It's very easy to kind of confuse yourself what way kind of things should be laid out. And obviously, it's also, once the dimension gets bigger, you end up with lots and lots of numbers. So you really don't want to work with them by hand, but sometimes it's nice to just see a simple example. A nicer way to kind of package all this information together is basically by presenting it as a multiplication table. So it contains the same information like the 3 by 3 by n by n by n, so n cubed array of numbers, but now they are written out as linear combinations of your basis vectors, and you basically just say what all the different combinations of basis vectors, E0 through En, multiplied, what vector does that result in? And it can be an arbitrary linear combination of the basis. So just to, again, step through it, because I'm not assuming that you have any background in particular. If I gave you this multiplication table on the right, and I asked you, how does this act, or like how does this multiplication work for two general vectors, x and y? The way that you could go about it is you simply write them out as these linear combinations, and then you multiply out, distributing over the multiplication, taking the first component of the first sum and multiplying it by the first component of the second sum, and so on. So then you get like a really long term like this. But then kind of the nice thing to do is to regroup things so that all your basis vectors are grouped together and all your scalars are separate. And then you can essentially just go and look up what each of these products of the basis vectors should equal to, and you can substitute them, and then you end up with your final result. So just to show that for one particular example, in this case, the most, like, all the interesting action happens in the second component. If you multiply that out, you end up with E1 times E1, and then you can look up in your table, E1 times E1 should equal negative E0, so you just replace that with negative E0, and then once you kind of regroup things, so you bundle together all the scalars, you end up with x0 times y0 minus x1 times y1. And yeah, so at this point, I may have given it away by going one step further, but the question I wanted to ask to the audience is whether anyone recognizes this algebra. I'll give you a little bit of time to think about it.
Complex numbers.
Yes, exactly. So this is just the old familiar complex numbers. The only thing I've done is renamed the basis elements rather than 1 and I. I've used the more generic E subscript 0 and E subscript 1. But yeah, once we make that substitution, it should look very familiar. And the nice thing is, in my opinion, that there's nothing magical going on with respect to the basis element I. It's just a vector. And if you multiply it out using the rules, you just end up with -1 times the first basis element, so -1. So you don't really need to speculate on, what are the properties. It's just how the multiplication was defined. And similarly, it leads to the natural question, well, what if we had an element that doesn't square to -1? What if it just squared to 1? And then we end up with another type of hypercomplex number, which are the split complex numbers. And just like the complex numbers, they are very well behaved, and you can see kind of the rules for multiplication on this slide. So I'm hoping that just by putting these examples in front of you, you'll get kind of some sense and some familiarity with how these numbers work.
Daniel,
yeah.
Given that you always insist that these things be unitary, will E0 always equal 1?
That's a very good question. Yes, so it's convention that if it is a unital algebra, then we usually put the 1 in the first position, and then we, but there's nothing in the hypercomplex numbers, or in particular, if you just take the K algebra as being an arbitrary vector space with a bilinear product, there is nothing saying that it has to be unital. So it's just that typically it's very useful to have a unit, and that's why I think the definition was chosen for the hypercomplex numbers to always be unital. But on the computer, you can also come up with some examples that don't have a unit by just picking random numbers essentially to put as the structure constants of your algebra. And then the question is, what can you still do if your algebra is not unital? There are interesting consequences. But there is one very famous example, which I will come to in a moment, of a K algebra that's not unital. So then, of course, you wouldn't have a 1 to put in the first spot. Does that answer the question?
Yep, thank you.
Great. Right, so just to give you an idea of what this looks like as we increase the dimension, so we just add more basis elements. In this case, I've called them 1A and B. And again, at this point, this should be looking familiar. We have this three-dimensional array of numbers, which determines how to perform the multiplication. And as you expect, kind of the multiplication rules work out just fine. But of course, the question is, what do these numbers mean? Like, how are they useful? Why should you care about them? So one reason why I've picked the names 1A and B is because this is actually an example from group theory. So this is the cyclic group of order 3. And then there it is conventional to use this labeling. And if you, so this is just to say that the hypercomplex numbers also kind of subsume, in a sense, groups. The only difference is that kind of groups are more restrictive, because in the multiplication table for a group, you can only put one element in each cell, versus in the hypercomplex case, you can put arbitrary linear combinations of elements in the cells of your multiplication table. So here I could also have something like A plus 2 times B, for instance. But otherwise, there are some similarities. And yeah, you can take any group that you want as your multiplication table, and it gives you a hypercomplex number. So that's an interesting, fun little exercise. Once again, the question is, of course, what does this mean? And how can I use this? So I think that's what I'll get to in a moment. But
there's a quick question about
yeah.
the multiplication tables.
Yeah.
Can we use the Kronecker product to streamline the matrix representation of the product using the structure constant matrix?
I'm not sure I follow exactly how you would simplify it. It's possible, but I can't
Ted, do you
quite.
want to elaborate?
It just occurred to me that it looks similar to that operation where you take the Kronecker product of the constant matrices and apply it as a matrix multiplication to the Kronecker product of the
Okay.
of the vectors. But it might not quite work out. It's the type of thing you physicists like to do with tensor product of entangled states, and it looked very similar to that.
Yeah, no, I think you're onto something. I think the Kronecker product does give you a way to construct hypercomplex number systems, and like you said, it's essentially the operation of tensoring, I believe. So yeah, there is a way to think about taking Kronecker products of these multiplication tables and ending up with higher dimensional algebras or hypercomplex numbers. So this is another fun exercise that you can do, is ask what are complex numbers tensored with themselves, or what are complex numbers tensored with quaternions. What kind of structures do you end up? And similar to the tensoring operation, there is also a natural direct sum of algebras where you essentially just put two of the multiplications tables into one big table and fill out the empty space with zeros. And yeah, both of these operations are well behaved and yeah, lead to some interesting results. So, but before we get too much into that, just wanted to summarize what we've just gone through in this short introduction. So if you are familiar with K-vector spaces, K-algebras are exactly like the K-vector spaces you already know and love, but they introduce this one extra operation, which is the multiplication, and it can be fully described using this multiplication table. And you end up with a whole big collection of these algebras that are all very interesting, and I would like to motivate that, it's worth looking into them and exploring them. And just to give you a heads up, we will get back to this in a second part later on, where I will look into different ways of denoting some of these operations and representing them in ways that are maybe a little bit more friendly and less kind of laborsome to write out all these big arrays of symbols. But the reason why I wanted to include those arrays is because they are kind of the closest to what these things actually look like on the computer when you implement them. So hopefully this gives you a sense of how you could go about it. But yeah, I still feel like I've given you a lot of kind of information, but not enough motivation why you should care. So here I want to give you some small examples which hopefully will motivate things better.
A quick question before the example.
Yeah.
Will only groups work, or can you use other structures for these multiplication tables?
That's a wonderful question. So in my case, I often end up with a multiplication table that does look like a group, essentially. The only difference is that sometimes elements also multiply to give 0, which that's also not necessarily something that happens in a group. And so a lot of these examples that are really kind of useful and interesting, they end up having these very simple multiplication tables. You rarely get examples where you have each cell containing like an arbitrary linear combination with arbitrary coefficients of all the basis vectors. Of course, there's nothing stopping you from doing that. You could just random number generate an n cubed size array, and that would be a valid algebra. But the question is that an interesting algebra? And how you decide whether or not an algebra is interesting, and whether maybe this messiness in the multiplication table is only like accidental, and maybe there is a transformation that you can perform to arrive at a more simple multiplication like this. That's something I'll get to later on in the talk.
I think it's worth noting with that algebraic number fields over the rationals are where you have where you basically look at any linear combination, but you have a bit more restriction on what can happen. So you have a sort of different sort of set of restrictions there to explore algebraic numbers.
Yes. Yes, definitely field extensions are also closely related. So all of these things that have a multiplication table and you add more elements to your field to extend it, they are all very similar in flavor. And I hope to draw some of the parallels. But like you say, I think the hypercomplex numbers in some sense are the loosest you can be while still requiring this bilinearity, but nothing else. Right. So are there any other questions before I go ahead?
Must they be semigroups? It seems to me that the answer is no, because they could be, because otherwise, let's see. You're talking about associative algebras or non-associative algebras? Earlier you said that they could be non-associative.
Not necessarily associative, not necessarily commutative. Essentially,
so a semigroup would be associative, but they don't have to be. If this table is replaced by a semigroup table, then that would mean that the restriction of the multiplication operation to the units forms an associative semigroup, and I don't see that that's a requirement.
Yes, I think that's correct. It's not a requirement. It's something that can happen, but is not required to happen.
Okay, and if it is a semigroup, does that extend to the whole algebra that it's
right? That's a really good question. I'll come back to that.
Yeah.
Yeah. Essentially, I mean, this goes in the direction of how do I know, given a set of structure constant, what algebraic properties does my algebra have? Mm-hmm. So I'll have a little bit on that later in the presentation. All right, so just for those who do need a little bit of visual motivation, here's an example. So basically in computer graphics, we are often interested in drawing triangles, as I was saying earlier. And let's suppose you wanted to draw this in such a way that you don't draw one line directly, but you draw several kind of points in between. So in computer graphics, we call that interpolation between 2 points in your space. So my question to the audience would be, if that was your goal, how would you go about it using the kind of mathematical tools that you're familiar with?
Linearity.
Yeah. That's a good answer. Any other answers? Any more elaboration on that, or?
Well, a linear combination of the two vectors, presumably, that are the endpoints,
Yes.
right?
Right.
Or,
yes.
To be more precise, a convex combination.
Right. Yes, I believe that's correct. That's what I was looking for. So we could just calculate the vector pointing from A to B, and then we scale that by a scalar t, and that gives us all the incremental steps in between for different values of t. So again, you could rearrange this formula in different ways if you multiply things out and then group things differently. But I think most people who have done some linear algebra will probably be familiar with this formula. So it's basically your starting point plus endpoint minus starting point times t. And I've written it slightly differently where I put the a, negative a in front. There's a reason for that. But let's move on. So the second level of difficulty that I have for you as a challenge here is, what if the triangle that you're trying to draw is not on a flat sheet, but on a sphere like this? Any ideas how you could generate these points connecting 2 points, the intermediate points that are on a line on a sphere? No one wants to go for it?
You do a spherical transformation of your coordinate system, and then you apply the same principle you had before.
That's a good idea. Yeah. That's one way to think about it. If you've done lots of computer graphics, you may also be familiar with the spherical linear interpolation formula. And if you kind of compare it with the formula on the previous slides, there are some similarities. But first, you have to kind of compute this angle. So the difference between A and B is not just a simple subtraction anymore, but you have this whole inner product and then arc cosine and some division by the lengths of A and B to get the angles, and then you can use this formula with a bunch of signs to compute the points, just like in the previous case for different values of t. But this was already a little bit more involved, I would say. Not the nicest formula to memorize. But anyhow, let's soldier on. What if instead of on the surface of a sphere, the triangle was drawn on a hyperboloid, on one sheet of a hyperboloid. Does anybody know the formula for that?
It's the previous one with the cosh and shine replacing sine and cosine.
Great guess. So people who are familiar with hyperbolic geometry, they might suspect that it has something to do with replacing the sines and cosines here in this formula with hyperbolic versions. And that's almost correct, the way I've written here. But there is a subtlety. And at least if you approach this naively and think about the dot product in the naive way, this will not give you the intended result. You also have to change your definition of the dot product and the norm in order for this formula to work. So it's not easy. It's a little bit tricky. So for the final level of difficulty, what if I wanted to draw the triangle on this funky trumpet shape? Does anybody want to take a guess at this formula?
Is it
I would imagine probably
is
not.
it the pseudosphere?
Yeah, so good question. I don't think it is. I have the formula for the surface. I don't think it is the same. But it looks similar. You could think of it as a kind of a black hole or something, where your space-time is curved. And everything
it's
is pulled into that.
It's not the plot of a Gaussian, a two-dimensional Gaussian curve.
I don't think it is. So the surface that you see here results from the what I call the triplex numbers, or the hypercomplex numbers with the cyclic group of order 3 as multiplication table. But again, I'll get to that in a little bit. But the point here is mainly that memorizing all of these formulas is not a lot of fun, at least not for me. And I don't even know what the formula would be for this case. But wouldn't it be nice if we could just use the simple formula that we started with on the very first example? Well, I'm here to bring you some good news. We actually can. We just have to do one little trick, which is to replace all the addition with multiplication, and similarly replace the additive inverse with the multiplicative inverse, and then instead of multiplying with t, you have to raise it to the power t. So basically, you're just lifting all the operations up one step from addition to multiplication, if that makes sense. And then suddenly this formula works for all the cases that I've shown. Of course, you may ask, well, what does this formula even mean? Like, what does it mean to raise something to a power of t? And what does the inverse of a mean? A is a vector, so how do I invert it? So those are all valid questions. I've provided a bit of a hint that we're going to need the exponential and logarithmic maps in order to compute this, but here I just wanted to give you this as a motivation, as using hypercomplex numbers, we can do this very natural operation using a very simple formula that works in a lot of weird and exotic curved spaces.
So
that's,
Daniel, that is we've just finished an hour.
All right.
So that's I think a really nice place to sort of finish the motivation maybe for this.
Yeah.
These ideas.
I'll go for one more motivation in case you're not like convinced, but then I guess we will skip some of the theory section later. But I do want to get to this part as well, because I think it will be of interest to some of the participants who are attending. So another really neat trick you can do with your hypercomplex numbers is, if you're given some well-behaved function, or in particular here, it's shown using a polynomial. If you simply replace your argument rather than plugging in just a real number, you plug in this special kind of hypercomplex number with the multiplication table here given on the right. And you just go through the motions and multiply things out the way you would according to the rules of the multiplication table. What you will end up with in the end is not just the value for the polynomial evaluated at a, which is the real part of your hypercomplex number, but also the value of the first derivative of the polynomial evaluated at a and scaled by b, but you can just set b to be 1. And in that case, you will get the first derivative for free, which is really nice. So you can use essentially the same definition, and simply by plugging in a hypercomplex number, the machinery works out in a way that gives you the derivatives for free, which is kind of the idea behind automatic differentiation. And this is just showing that, well, what if you say that squaring epsilon to 0 is not very nice? You would like to keep epsilon. You can do that too. You just need a bigger, higher dimensional hypercomplex number, which also includes epsilon squared as a basis element. And in that case, the same trick works, and you end up getting the second derivative as well at the point x0.
So
You get
may I
it divided. Sorry,
Sorry,
yeah.
may I suggest this is a good time to finish the live stream and I think if people want to stay on, I think there's lots more stuff that Daniel can tell us, but finish the formal part of the talk here. So let's all thank Daniel for very
Okay.
interesting discussion.
So just a sneak preview here, we would have also looked at partial derivatives and then more theory to come, but maybe that's something for part 2.
Or I started thinking that I could represent what John Bell wrote in his book, A Primer of Infinitesimal Analysis, for students instead of requiring category theory and Topos theory in order to understand it. And I just thought, well, why don't I try to do something like non-standard analysis, but with matrices. And so I took the epsilon in that example to be a 2x2 real matrix with a 1 in the top right corner and zeros elsewhere. And I just declared that that element is less than any element of 2x2 matrices with real number entries and diagonal a diagonal matrix with constant real numbers, the same real number on the diagonal. So a multiple identity. So I declared it to be less than that, than all of those. And that makes it an infinitesimal in the non-standard analysis sense, in the Leibniz sense. And then if you form a ring, it's the subring generated by those guys.
Yep.
And then you can do this automatic differentiation with matrix multiplication. So you can teach this to college algebra students who just learned how to multiply matrices, for example. I was teaching linear algebra at the time, but our linear algebra curriculum is rather strict, and we have topics we have to cover, and giving the students extra things just ended up with kind of they felt it was too much and they don't like to do it. So
yeah, that's unfortunate. Yeah, I think that this material is not very well covered in the standard curriculum. At least it certainly wasn't for me. I had to find it myself from various sources. It's just outside the scope of what most people learn about when they take a linear algebra class, and I think that that's quite unfortunate. There are other, specialized aspects, like, of course, people learn about analysis and complex numbers, and these days Clifford algebras are also somewhat well known and popular in the broader kind of public, I guess. But there are, this very high level view of the hypercomplex numbers, I think, is not very well taught.
Yeah.
And there are lots of useful applications in my
So to get this kind of application I'm talking about, you need a representation of your algebra. And so that led me to think about representation theory a little more, because I'd never really covered it very much before that.
Right.
But the thing is,